Lesson 5. Divergence, Conductor. Section 5.2. Conductor. This is a spherical conductor. Assume that a cluster of electrons is placed into the conductor. What will the charge distribution be? Electrons repel each other, and move to the surface of the sphere. The input electrons will be evenly distributed on the surface of the sphere, and there will be no input electrons remaining inside the sphere. In the actual case, the number of input electrons is very large. Therefore, the electrons cover the entire surface of the conductor evenly and continuously. A sectional view looks like this image. The thickness of electrons layer can be considered as 0. If all the input electrons settle on the surface and do not move anymore, this condition is said to be static. Let's examine the properties of the static electric field inside and on the surface of the conductor. The radius of the sphere is a meters. Inside the conductor where r is less than a, the electric field intensity is 0. If it were not 0, electrons in the conductor would move, meaning that it is not a static situation. On the surface of the conductor, the electric field intensity E is normal to the surface. AN is the unit normal vector. If it is not normal, then the component of E parallel to the surface will force electrons on the surface to move. This is not static. The surface is equipotential, because E is normal to the surface. This property does not depend on the shape of the surface. On any curved surface, E is normal to the differential surface. Exercise 5.2.1. Pause the video, and answer the problem. Find the static electric field intensity E and the potential V inside and outside the sphere. The answer to exercise 5.2.1. This is the case where r is less than a. CS1 is the closed spherical surface with radius of r. According to Gauss's law, E on the surface CS1 is 0, because there is no charge inside the volume enclosed by CS1. Thus, E is 0. Next is the case that r is greater than or equal to a. According to Gauss's law, the area integral of epsilon E on the surface CS2 is equal to the charge inside the volume V2. Thus, E is obtained as this equation. The potential at r, which is longer than or equal to a, is found as this equation. Inside the conductor, V is constant at the surface potential, because the electric field intensity is 0. Exercise 5.2.2. Pause the video, and answer the question. Find the static electric field intensity and potential at these three regions. The answer to exercise 5.2.2. On the inner surface CS1, electrons are attracted by the positive point charge q coulombs, and are evenly distributed over the surface. The electric flux lines leave the point charge, spread radially toward the conducting shell, and terminate on the electrons. The total charge on the inner surface CS1 is negative q coulombs. On the outer surface CS2, positive charges of q coulombs are attracted by the negative charges on the inner surface CS1, and are evenly distributed. The electric flux lines leave the surface charges, and spread radially toward infinity. Although discrete images of charge distributions have been shown, in the actual case, the charge distributions are continuous on both surfaces, and the thickness of the charge layers can be considered as 0. This is the answer to exercise 5.2.2. Pause the video, and check the answer. Exercise 5.2.3. This is your homework. Pause the video, and answer the problem. Section 5.3. Electric field at conductor surface. A spherical conductor is charged, and the surface charge density is ρ coulombs per square meter. A cylinder is placed across the surface of the sphere as shown in the figure. dCSC represents the closed surface of the cylinder, and dVc represents the volume inside the cylinder. The top area dSC1 and the bottom area dSC2 are differential areas. The circumferential side area is denoted by dSC3. The height of the cylinder dLc is very short, so dSC3 is also a differential area. The electric field intensity E is normal to the conductor surface. No electric field lines cross the circumferential side of the cylinder. E inside the conductor is 0. Thus, according to Gauss's law, the electric field intensity on the conductor surface is given by this equation. By defining a unit vector AN normal to the conductor surface, the vector E is expressed by this equation. Exercise 5.3. This is your homework. These arrows indicate the directions of Cartesian coordinates. The circled dot indicates the x-axis. It is perpendicular to the slide, and comes out of the slide towards you. Then, suppose an infinite plane charge parallel to the xy plane, with a constant charge density of ρ coulombs per square meter. Pause the video, and answer the problem. This is a brief summary. In this lesson, we learned about the divergence.